Robots are fun to watch, but we want to know more. How do robots work? Figuring this out is mission critical for anyone interested in what is arguably the most exciting field of technology on the planet. When we watch a robot like Baxter, the body of the robot is the natural place to start our investigation. But we need to ask ourselves this prequel question. How do we figure out how a robot works? We're talking about methods here, ways and means. And there are two different methods that scientists and engineers employ: analysis and synthesis. Roughly, analysis translates into taking stuff apart. Scientists do a lot of this. We take apart, we dissect, we destroy in order to build a broader understanding. Synthesis translates into putting stuff together. Engineers do a lot of this. They design, assemble, build, and construct. Now, even though analysis and synthesis are different, they're entirely complementary ways to figure out how something works. This pair of approaches may sound familiar if you've ever seen the TV show Destroy, Build, Destroy, where teams take apart a familiar object like a car and then use the parts to build something new. So robotics really needs both of these approaches. Neither the scientific nor the engineering approach is better. Engineers need the scientists' understanding of what the bits and pieces are and how they work in order to build something, while scientists need to have instruments and devices designed and built by engineers in order to take new stuff apart. And engineers can tell the scientists when they need to know more about the parts. All right, I know that taking stuff apart can be hard psychologically. What if you break it? Well, let me tell you this. There's nothing like getting your hands dirty, and I'll show you now how to do that. We'll use the analytical approach and do something incredibly fun and potentially foolhardy. We'll take apart a robot. We'll disassemble a Roomba and create a parts list and see what robots are made of. I should warn you, do not try this yourself unless you are willing to void your warranty and replace the entire robot. This first bit of robot analysis will let us see for ourselves that robots are composed of sensors, actuators, controllers, and an energy supply, all of which get housed in a body. So let's take a quick look at Roomba on the job. What does Roomba do? Roomba lives to serve, scooting around the floor, cleaning up dirt, dusting, and vacuuming. Okay? But we need to keep in mind that Roomba's basic reason for being is to do exactly this. Its goal is to keep our floors clean. So knowing the overall design goal is really important before we get started to dissect something, because all the parts in the body have to sum up to allow this to happen. All right, I'm going to turn off Roomba here. And we're going to bring Roomba to the table. Told you this is going to be hard to do. We have this beautiful robot and we're going to take it apart. So for regular maintenance, you actually have to be able to take parts of Roomba apart. You need to know how to clean the dust bin. Okay, so here's the dust bin, which contains the dirt that you're going to empty. Let me flip this over, and I'm going to pull off this cover here, and then the brushes come right out. So there, just regular maintenance. We're already starting to get inside Roomba. We're going to return to that, okay? And let me see. We've got the motors here that spin the brushes. So they're in the inside. You can see the wheels, which we'll get back to as well. And we have this outer brush. Okay, so internally there's also a fan system, which is sucking up the dirt and putting it in the bin. And that's the grand central station of Roomba. What we're going to do now is dig deeper. So what else does Roomba need to do its job? It's got brushes, it's got dirt collection. Well, this 5th generation Roomba is designed to have replaceable modules. To access these modules, we have to go through Roomba's soft underbelly. So we're going to start here by taking off this side brush, like so. And when we take stuff apart and we have any hope of trying to put it back together, what we want to do is keep our parts together. So I'm going to take off this screw, and I don't want to confuse it with any of the other screws that are going to come out. So there, I've pulled off that brush, I'm going to put the screw in there, and I'm going to take a little piece of white electrical tape that I have here and put that over the brush and the screw so we keep our parts together, like so. All right, so I haven't lost that screw and I know exactly what it goes to. All right, so that side brush, by the way, helps flick particles of dirt into the main mouth of Roomba. So you can think of that as a little hand that's over there taking crumbs from the side of the room. All right, now there are 4 screws, 1, 2, 3, and 4, that we need to loosen to get this bottom cover off. Yeah, actually, that's great. Those screws stay in there, so I don't even have to put them in my pillbox. They're going to stay in place. Okay, aha, and look at this. We're already seeing really cool stuff underneath. So back to Roomba. Here's the battery. This is a nickel metal hydride battery, a very common and safe type of rechargeable battery, and it came into use during the 1990s. Now I'm going to pull it out, but before I do, I'm going to do what I told you before, which is I'm going to take a picture of it. And I'm going to do this because even though I think I have a great memory, one is never sure, and I want to make sure when I put it back in that I'm putting it back in the proper orientation. So it's got little tabs here, and I'm going to yank it out. So here's the battery. You can actually see the connections here for the battery. So if we look inside Roomba, right here, you can see where those connections on the battery are making contact to power Roomba. Okay? Now, there's something that's not really meant to be removed. The front trim piece here of the bumper. This is not listed as a replaceable module, so meaning if you break it, you'll have to replace the entire robot. If you break it, you keep it. You own it. It's yours. So we're going to go ahead and loosen these screws and be daring here. Off now, right here. And what I've got here, you can see the front bumper. You can see some switches there. These are springs that the bumper adheres to here, okay? And this is going to come off. And there's a wire right here that goes out to the bumper. Now that wire is actually a telltale sign for us. It means that there must be some kind of electrical sensor here out in the bumper. Okay, this is not just a simple passive device. Now I'm going to flip this over, and you can see over here where that wire comes into play. Now to get the frame off, which is this top frame off, this gray part, I can start to peel it, but I'm going to have to put a screwdriver in here in this gap, which is a little crazy, and pop it off like so. Okay, let me put this over to the side. So this reveals this top deck here. Good to go. You can see that right under the top frame is what iRobot calls the top cover, and it's securely held in place by 11 screws. So we'll need to remove those screws and put them in their own labeled container. By the way, I forgot to label this container, which was for, we'll close that up now, and that was for the bumper. I'm using an indelible ink marker, by the way, in case we get a sudden rainstorm here in the laboratory. And this is going to be for the top cover that we've just decided here. All right, we're all ready to go. And I'm going to try now the regular screwdriver. So this is great. So we have the screws off here, and now I'm going to pull this top cover off. I can use these spots right here as a purchase for my thumbs, and then I'm going to lever off the white cover part. Here we go. It's one side, and there's the other side. Okay. Oh, and I see that there's one screw that I missed right here. That's okay, I haven't broken anything yet. There we go. All right, so we've got that top cover off. Now, put that to the side here. There we go. So I have to be careful because of this wire that we talked about here. So I really should pull it out. What's really neat is you can see now what's happening with that wire we talked about with that bumper. It's definitely coming in and talking to this whole portion of the robot, which is the motherboard. So I'm going to very carefully pull this out. There's a connector here. And I'm actually going to use a pair of forceps, which will give me a little more purchase on those wires. And so I'm just going to, these are actually kind of forceps that are locking. So I can just pull that out. You can see there? Ta-da. And so there's the connector. Now, this is an area that I'm likely to forget about. So I'm going to take a picture right there of where that connector is coming out of on the motherboard. Okay, so we have that documented. I'm going to unlock my locking forceps here and put them back. So this is really neat, right? I'm going to set this bumper to the side. So this main platform here contains the computer and the other electronics that take signals in from the sensors, process those sensors, and then send signals to the motors that drive Roomba and sweep up dirt. So this motherboard has a load of wire connections that don't come off easily, as you can see here. Now, I'm going to flip Roomba back over and unscrew the left and right wheel modules here. Okay? And when I do that, we're going to see further down into what is in the housing. So this is great. So here is the wheel module. And what I'm trying to do is shake out the screws. We'll leave them in there. That's not going to come out. So you can see right here, there's the motor that drives the wheel. The motors, we've already seen, the wheels are spring-loaded, which you can see here. Now notice when we're looking at the wheels, that each of these wheels has its own motor. There's no steering mechanism down here. But we clearly saw Roomba turning. So you're probably guessing how this works, right? It's a process called differential drive or differential steering, where each of the two wheels has its own motors. Make one go faster and you turn about the other. Now to avoid confusion with a differential in a car, some roboticists prefer to call these differential wheeled robots. Either way, it's a very common design in terrestrial robots. And let's go ahead and remove whatever this thing is over here on this side, which is by our motor module. Remember this? This is actually the motor that we're taking out here for the brush. Okay, so here's that motor that I've just taken out. And you can see the motor on the back end here. So here's the motor that runs this brush on the side. So we'll put this motor, we've been having our motors over here. Okay, and then we have this final wheel module, which we will take out because we're almost there. Aha, there it goes. Okay, so that doesn't come out. So this is another motor for us here. All right, so we have Roomba taken apart. We were working by analysis here to understand it. And one of the great things about any autonomous robot is that we find that they have 5 different categories of items that go into their build. So we've talked about motors and actuators, and our individually motorized wheels are very obvious actuators here. We have another motor that we talked about for our brush, and in the brush housing for the main brushes here, we also have a set of motors that are driving these actuators that are doing the actual cleaning, along with, there's another motor that you don't see here that's actually in the body that is driving the vacuum cleaning and pulling the suction through as well. So we've got lots of motors to make things happen. Now on the sensor side of stuff, we've started to dig out some pieces of that, and we began by noticing this wire here. Well, it turns out this wire, if we flip this over, actually goes to that sensor here, which is right up here, and it's a little IR beacon, which will be important in just a second to explain what's going on with that IR sensor. and how that's operating. We noticed on the front of Roomba here when we took off that bumper that there were switches. So those switches initiate the escape response that Roomba has. And we had noticed a bunch of wires up here, and it turns out that there's a band of sensors right here which are involved with what's going on in the bumper. Now I'm not going to take this off because it's really finicky, but you can see again the telltale sign when we take it apart. There are all these wires that are going into the motherboard. So this is a bunch of sensors, and you can see there are little teeny, almost like little eyes here. This is a whole array of IR emitters and detectors. And here's the cool thing. You can't see it, but I can. If I do my Geordie LaForge, I can actually see through the bumper here. And there's our actual little windows through which those IR emitters and detectors can work. So those are windows up there, and that allows Roomba to not hit things, but actually avoid them using that whole array of IR emitters and detectors on its bodies. So we've got some really cool sensors here. We also have a third category of part that goes into our robot, and that's the energy supply. And we have the elements of the body as well as a kind of fourth category here. And then we have the computer itself, which we talked about being here on the motherboard. And we see with all these integrated circuits, all the different kinds of control and processing that go into the Roomba. So those are the 5 major categories of any autonomous robot: sensors, actuators, controllers, energy supply, and body. Now, truth be told, most robots don't exist just as a robot. They're part of a larger system. And that is definitely true for Roomba. Roomba has a couple of different parts of what we'll call the support system. It has, if I turn this on here, it's got a landmark system that allows you to tell Roomba where you don't want it to go. This is just something you set out in the world, and it can block off a door. It's called a virtual wall, and it can also function as a beacon to get it from one room to another. We've got a power supply and docking station here, so when Roomba finds its way home using this sensor, okay, this is the IR receiver that I mentioned we'd get back to, and there's a beacon here on the charger, and they can talk to one another, and Roomba can use that as a homing signal. And also, we have a remote controller. You can buy remote controls for Roomba, both for programming it, and in this case, you can also drive it around. So these are the basic elements here of any robotic system, which includes a robot and its support system. Now, as soon as you, the human, remotely control a robot, it's no longer autonomous. A human is in the functional loop, making decisions in place of the robot's controller. In fact, a human is almost always in the background. Maybe only in the deep background as another part of the robot support system. When and how a human enters the control loop is always important. That's why many robots have a built-in ability to be both autonomous and remotely controlled, like Roomba. I'm going to remote control here and tell Roomba with my IR communication system to come on, off, and clean. And now Roomba is operating here autonomously. I have a virtual wall set up that's going to tell Roomba not to go any further there into the laboratory. And let's look at some of the sensors that we investigated. There are those bump sensor switches, those 2 little black switches that we saw when we took Roomba apart. Roomba's very carefully cleaning around my feet here, which is nice. And what else do we have? Let's see if there's some object avoidance. Now what I'm going to do here is remotely, actually I'm going to push a button, which is another way to communicate with a robot, and I'm going to tell Roomba to go dock. This should show us the communication between the IR sensor here and the IR beacon that's right here. So Roomba is in a mode here to be looking for that beacon signal. Okay, so Roomba is hunting for the signal here from the charging station. It's found it, and now there's a routine using negative feedback control where it's going to work its way into the homing station for charging. Perfect. As with any animal or robot, evolving or designing it for a particular task involves trade-offs. You can't do everything well. So while Roomba does its job cleaning floors really, really well, even transitioning from bare floors to carpeting, it's not built for moving up and over or down and over steps or drops. In fact, it has those cliff detector sensors we talked about to keep it from tumbling downstairs. So think of the trade-off like this: clean but not climb. You might think that this is not really a problem, not a trade-off if Roomba never encounters stairs or other obstacles. Fair enough. But many domiciles have stairs that lead to other places you might like Roomba to clean. What's the short-term solution? Well, you can get a Roomba for every floor of the house. I'm sure iRobot would be very, very happy if you did that. But that's expensive, and it still leaves the stairs unclean. With stairs and other obstacles in mind, iRobot, the maker of Roomba, has designed a different kind of robot, PackBot 510. Right away, you can see a very different kind of body. PackBot has tracks instead of wheels, and it has a compound track with a joint in the middle that lets it get upstairs. When it approaches stairs, that front track gets tilted and levers the robot up the stairs. Once on the stairs, the tracks themselves are of the length that they don't experience the treads of the stairs. The design of PackBot's body converts the stairs into an elevated track. But there must be trade-offs, right? There always are. Well, you can see the difference in size right away. PackBot isn't going to be cleaning under your furniture. So we can think of the trade-off being the opposite of what we saw for Roomba: climb, but not clean. Unlike wheels, tracks don't get caught in the pits and valleys of uneven terrain. Just like with stairs, PackBot's tracks are great for moving over debris. PackBot was the first robot to investigate the aftermath of the Fukushima nuclear disaster. So we can think of a trade-off now at the level of actuators. Wheels can be small and take up just a small part of the body. Tracks tend to be larger and take up a larger part of the body. So one trade-off for these actuators is between size and traversability. Do we see trade-offs like this in other robots? You bet. As I said before, trade-offs are built into any design. Let's see if we can spot the trade-offs in other robots. What about aerial robots? What about drones? Well, the first thing that I notice about a drone is that the body is the actuation system. Propellers, 4 of them. Also, the body is very lightweight, so right away it looks like a system built for flying. It's a quadcopter or quadricopter, where the quad stands for 4 propellers. One of the very nifty things about quadcopter drones is that they are highly maneuverable. They can hover, flip, twist with ease. That's why a drone can be so good for taking aerial pictures. It may even have a whole cinematography mode built in. Let's compare with a fixed-wing aircraft, what we call an airplane. Helicopters suffer in terms of energy requirements. A plane generates lift by moving its wings forward, while the helicopter uses propellers. So a robot body designed as a helicopter or a quadcopter, we can state a trade-off in this way: maneuverability versus efficiency. What about trade-offs in the designs of robot bodies in the water? This is Tadro, a very simple surface swimming robot that we've built at Vassar College. Tadro is built to seek light, and I'm going to turn it on here and you can watch how it's going to work. I'm not going to put it in a tank right now, but Tadro has a single eye spot. It's very, very simple, and a single servo motor. So the servo's job is just to wag the tail back and forth. And it's going to respond, the servo, to changes in light. So I'm going to put my hand over the light and just see the tail turn there. So this is about as simple as you can get when you build a robot that is autonomous. Take my hand away and it's going to turn to the other direction. So what's going to happen in water is Tadro is going to swim around and tend to swim towards a light source and swim away by turning its tail from an area that's dark in the tank. Now contrast Tadro with robot Madeline, also from my laboratory at Vassar. You can see in this clip how agile and maneuverable Maddie is. Looking at her flippers, these are actually 4 flexible actuators. They're all under independent control, and different combinations of action from the flippers allow Maddie to swim forward, or roll, or pitch. Beautiful. Tadrow also swims with a flipper, but just one. So we aren't talking about the difference between wheels and tracks here. Tadrow is very small, not very fast, not very maneuverable. We love you anyway, Tadrow. Tadrow just swims on the surface of the water. Compared to Robot Mandolin, Tadrow shows simple, slow behaviors and is built with only a few components. So the trade-off for these two water robots is simplicity versus speed and maneuverability. So far, we've focused on differences in locomotion: tracks, wheels, propellers, flippers. For mobile robots, which are built to move themselves around, the needs of that mobility drive, if you'll excuse the pun, the design of the body. But there are other robots called static robots, stationary robots, or manipulators. And these, like Baxter, stay in place and move objects rather than themselves. Baxter is a super cool kind of robotic manipulator. It has two arms, actually two manipulators, as you can see here, and Baxter can do a type of task that's very important in many industrial situations. Pick up objects and place them somewhere else. Let me show you this happening. Get Baxter going here. So this is called pick, wait for it, and place. Packing, unpacking, sorting, and supplying are all jobs that involve picking and placing. So picking and placing is what we humans do when we reach for and grasp and move an object. And this gets us thinking about hands as graspers and arms as, well, arms, right? Very fine and accurate picking and placing in 3 dimensions requires many joints. Look at Baxter's joints. See how every reach and every place involves the controlled movement and coordination of the joints. Now, let's see, same with me. If I want to help out here, and I will in just a second, and unpack the box that Baxter has so painstakingly packed here, then I have to rotate my shoulder, my elbow, and my wrist and fingers in a particular pattern in order to pick it up, okay? So for roboticists, the human arm has been a source of inspiration for a long time. If a joint, like a hinge joint, like my elbow, can only bend in one plane, we call that 1 degree of kinematic freedom, okay? And that's in engineering terms. My shoulder joint, though, is much more complex. It's a ball joint, and I can elevate, depress, abduct, adduct, and then rotate and create very complex movements with a single joint. Now, how many different degrees independently of freedom does my shoulder joint have? It actually has 3, since I can rotate in 3 different ways. Hey, well done, Baxter. All set here. So now when we think about joints in the human body, we almost always talk about rotation. But we can talk about another kind of kinematic degree of freedom, and that's in translation. Let's take a look here at Baxter's manipulator. So these are Baxter's fingers, okay? And let's see here. Baxter's fingers, and you can see they can open and then close. And they're moving on a linear track, and so they have a single degree of freedom in translation. Degrees of freedom look great. More degrees, more maneuverability, more space that can be reached, and more different kinds of objects to be handled. Any trade-off here? Yes, indeed. Each one of these degrees of freedom needs its own motor. More motors mean more power consumed. Also, more degrees of freedom means that the mathematics of coordinating the whole motion of the arm becomes more complex. So more degrees of freedom mean that you need a bigger and faster controller. No matter what the robot is, you always see trade-offs. So this is really a key point when it comes to understanding how robots work. Can you see the trade-offs? But another way to think about trade-offs is to recognize them in the robots that you are building yourself. This is the value of synthesis, understanding by building and understanding that you're always designing trade-offs into your project. Now let me take you through building a Tadrow very quickly so you can see this in action. You've seen the intact Tadrow here, and let me just show you what it looks like when I take off the lid that preserves freshness. Inside we have an Arduino microcontroller. This is an Arduino Uno, a beautiful microcontroller to get started on. They cost about $50. We have a switch here There's a fixed resistor and a photoresistor here. And then we have on the back a servo motor that drives our tail. So that's what it looks like when it's complete. If you were to build this yourself, which I encourage you to do, because it's very simple, you just need to get yourself a suitable food container, a light-dependent photoresistor that you see here, a fixed resistor. I use one here that's about 10 kiloohms in resistance, some kind of tail. So this is just a piece of plastic and another piece of plastic that I've put together. Here's what the Arduino Uno microcontroller looks like, and a very simple servo motor. I also have here a power supply, an energy supply, and this is just a USB energy supply, so you can also do it with a battery. So those are the basic ingredients that you need to make a Tadro. It's very simple. And with that in mind, though, what we've chosen here for materials sets up the trade-offs that we've been talking about. First of all, you can see here that by putting a lid on, I haven't really made it waterproof. Water can still get in, but it just has a kind of splash guard for it. Let's think about the trade-offs. First and foremost, when we change the environment from water to land, the nature of how we locomote changes. We have to make a decision about how we're going to propel and steer. So what do we learn from this kind of analysis and synthesis, taking apart and building about how robots work? We see more clearly that the 5 categories of parts are really important. Actuators, sensors, energy supply, controller, and body, and they all drive our decisions. There's a 6th category for the support system, and that can change the way that the robot physically interacts with the world and includes communication systems and chargers, as we saw. So overall, the need to move dictates how the body is built, what kinds of parts it has, and how the controller needs to be programmed. So robot bodies teach us a universal lesson about how robots work. There are always trade-offs. The need for movement and the kinds of movement needed drive the design of robot bodies. Robot is as robot moves.